In today's video, we are going to look at calculating binomial probabilities, and then we're also going to use a Venn diagram to find intersections and unions between two sets. And then lastly, we're going to use Venn diagrams to find individual probabilities. So to begin with, we're going to look at the following problem. A fair coin is tossed 3 times. We're going to list the possible outcomes. So we could either get all heads, or we could get all tails. And then we could get heads, tails, heads, 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 tails, and tails, heads, heads. So those are the 3 outcomes there. And then I could also get it with 2 tails. So tails, heads, tails. Oops, tails. Well, we'll do heads, tails, tails, and then tails, tails, heads. So there's 8 different possible outcomes for this. All 3 heads, 2 heads and 1 tail in different orders, 2 tails and 1 head in different orders, and then lastly, all tails. So if you notice, the ratio of the possible outcomes for flipping the 3 coins is 1 to 3 to 3 to 1. Okay? 1 in this category, 3 in this category, 3 in this category, and 1 in this category, which gives me a total of 8 possible outcomes. So we can calculate the probability of each of these occurring by looking at a tree diagram. So initially, when I flip, I can look at either heads or tails. So I have a 50% chance of getting a head and a 50% chance of getting a tail. If my first one is a head, then I flip again, and I can either get a head or a tail. 50% for each of those. Tails, 50% head, 50% tail. And then lastly, because I am flipping it 3 times, to get another head, another 50% or 50% for the tail, 50%, 50%. Sorry, it's getting kind of hard to read with my halves. 50% head, 50% tail. And if it was a tail, 50% head and 50% tail. This is the downfall to making a tree diagram if you don't give yourself enough space. So therefore, my probability for each of these going across, heads, heads, heads. So if I'm going to look at this probability, the probability of getting each of those is 1/2 times 1/2 times 1/2, which is 1/2 to the 3rd. And then all the different combinations of 2 heads and 1 tail. Just move this off to the side. 2 heads and 1 tail, or a head, tail, head, or a tail, head, head. There's 3 of those. So the probability for each of those individual cases is 1/2 squared times 1/2 to the 1st, because there's a 1/2 squared gives you the heads, and then 1/2 to the 1st gives you the tails, and then there's 3 of those occurrences. Same thing works with 2 tails. 3 times, I only have 1 head this time, so it's 1/2, and then 1/2 squared. And then for my last case, it ends up being 1/2 to the 3rd. What we're looking at here are binomial probabilities. Either one thing's happening or another thing's happening. Either this is your outcome or that's your outcome. It's nothing that can fall possibly in between. With these binomial probabilities, we can also look at situations where they're not fair. So for instance, we have a coin that's weighted, so now the probability of heads is 1/3, while the probability of tails is 2/3. So we kind of have to keep these straight a little bit. So in that first case, when it was all heads, it's going to be 1/3 now, and there's 3 of them. Or if there were 2 heads and 1 tail, it's 1/3 to the 2nd, and then 2/3 to the 1st. And there were 3 of those cases, because there's only 1 of the 2/3. And then if it was 1 head, it's 1/3 to the 1st, and 2/3 squared. And then there was 3 of those occurrences. And the last one, there were 3 tails, so it's 2/3 to the 3rd. So if I can calculate each of those individual probabilities, I add those all up. Those are all my possible situations that can take place. Therefore, one of these is certain to occur. So if I add all of these probabilities up, it has to equal 1. Okay, so you can find each of those individual cases and add them all together. So we should kind of take a look here. There's some patterns that take place. If you notice, coefficients first. There's no coefficient there, so we're going to call it a 1, and there's none here either. So it's 1, 3, 3, 1. I'll bring you guys back quick to Pascal's triangle. Those are the coefficients in Pascal's triangle. Those are individual combinations, the different ways that they can occur. The next thing that you should see is I have 1/3 to the third, 1/3 to the second, 1/3 to the first, and most likely 1/3 to the 0, which is 1. Then I'll start at the end, 2/3 to the third, 2/3 to the second, 2/3 to the first, 2/3 to the 0. Dropping by degree and increasing by degree. So the probability, P of, the probability that A occurs X times and A not happening, occurs N minus X times, so if you go back, this is a 0, that's 3 times total, 2 and 1, 1 and 2, 0 and 3. We figure this out by N choose X of P to the X and Q to the N minus X, binomial distribution. But now keep in mind we're doing probabilities. The probability of this occurring equals the probability of it occurring and then the probability of it not occurring to the rest of them. N choose X is N factorial over X factorial N minus X factorial, if you remember combinations. So here's our story problem. An archer has a 90% chance of hitting the target with an arrow. If 5 arrows are fired, determine the probability generator and hence the chance of hitting the target. Part A is twice, and then part B is at most 3 times. So let's look at this initially here. So we're going to be hitting it twice. We want X to equal 2. So if X equals 2, we're shooting the arrow 5 times. So it's 5 times, and we're choosing to hit it twice. The probability of hitting it each time is 0.9. So that's 0.9. We want it to hit twice. So that's squared. Therefore, it's going to miss the other 3 times. 0.1, therefore, to the third. And then when you calculate this, 5 choose 2 is 5 factorial over 2 factorial, 3 factorial, which is 10, times 0.9 squared times 0.1 cubed is 0.0081. So the probability of hitting it exactly twice is 0.81%. This differs from at most 3 times. So if it's at most 3 times, then we want X to equal 0, 1, 2, or 3, because it's at most 3 times. So then I have to do all of these 0, 1, 2, and 3. So I already calculated 2 over there, but I still have to calculate the rest. So therefore, if it's 0, if you think of Pascal's triangle again, if it's 0, it's going to end up being 1 as a coefficient. So it's 0.1 to the 5. Plus, since it's 5 going through Pascal's triangle, the next coefficient is 5. And then it's 0.9 to the first and 0.1 to the fourth. Plus, the next coefficient is 10, and then it's 0.9 to the second, and then 0.1 to the third, plus 10, 0.9 cubed, 0.1 squared. So that adds up each of the individual pieces. So this is for hitting it 0 times, this is for hitting it once, this is for hitting it twice, and this is for hitting it 3 times. So when I add all of those up, I get 0.0815. So the probability is 0.0815 or 8.15%. That's the harder way to do it. Easier if you think through it. you want it to hit at most 3 times. We're only shooting at this 5 times. So therefore, I really just don't want 4 or 5. Since if I add up the entire sum, it has to equal 1. So the easiest way to do this problem find the probability of it happening 4 times and the probability of it happening 5 times and subtract all that from 1. What you're doing is you're finding the complement to it. I only had to find 2 of them versus 4. A little bit easier way to go through it. Now, sometimes some of the ones that we're going to calculate are going to take a lot of time. So we're going to be able to use our calculator to help shorthand some of this. There are 2 different things we're going to use in our calculator. There's a binomial PDF, and then there's a binomial CDF. The binomial PDF is used for an individual probability. For instance, I want to find the probability of hitting the target 6 times if I shot at it 105. Something like that. That's what a binomial PDF finds. It finds one specific probability. Versus the binomial CDF is for cumulative probabilities. So in the previous problem here, we're looking at most 3 times. So we wanted 0, 1, 2, or 3. So that's cumulative. I'm finding all 4 of those cases. It is important to note it starts at 0. So in that previous problem, I could have used the binomial CDF from 0 until I wanted at most 3, so from 0 to 3. So in order to do this, you're going to use your graphing calculator. So bring out your graphing calculator. You are going to go under second, and then the vars. And these bring up all the different types of distributions. This is a binomial, and we'll start with the binomial PDF. So on mine it's A. Hit enter. Now it says number of trials. So first we're going to look at the number of trials. So we're going to use the arrow problem. We have 5 times we're going to be shooting this, comma. And then the probability of success. The probability of hitting the target is 0.9. So comma, and then 0.9. Comma. The number of successes. So in the very first problem we wanted 2 successes. So then I'm going to hit a 2. Technically you should close your parenthesis, hit enter, and it gives us the probability of getting exactly 2 successes. The other one is the binomial CDF, which again is cumulative from 0. So if I want from 4 on up, I'll have to find from 0 to 3 and subtract from 1. I'll have to do the complement to it. But in this case, again, we want it at most 3 times. So to do this, second vars. This time we're going to go to binomial CDF, cumulative. Enter. And again, the number of trials, we're shooting 5 times, comma. Probability of success is still 0.9, comma. And the number of successes, the last success I want is up through and including 3. Close your parenthesis, hit enter, 0.08146, which is the exact same probability that I got when I did it by hand. Now, this isn't a whole lot of things to add up, so it might not take you very long to go through these, but it is definitely helpful if you're doing multiple items. So that's looking at some of your binomial probabilities. We're then going to move on and take a look at sets and Venn diagrams. So looking at these, they consist of a rectangle, which represents the complete sample space, and then the circles within them talk about the individual events occurring. You should have all seen Venn diagrams in the past. So in this case, we're looking at the sample space of rolling a die. The event A is a number less than 3. So the part that's in the green there is the actual probability that I'm looking for out of my entire sample space. A is inside, therefore the yellow is the complement of A naught. Okay, so taking a look at some of these different situations. So A naught was that shaded yellow which is the complement to the green, it says it doesn't occur. So therefore, if I take the probability of A and the probability of A not occurring, that has to equal 1. So we take a look at some individual situations looking at some letters. So U is 1, 2, 3, 4, 5, 6, 7. A is 2, 4, 6. Therefore, A not is the ones that are not included in that are 1, 3, 5, and 7. So just a little bit of terminology. A, X is in A, means that X is an element in the set of A, and then N of A is the number of elements in set A. So just some notations as you're taking a look at them. Union. So now we're going to take a look at two different sets overlapping. Okay. So the U, A, U, B, denotes the union of the two. So it talks about all the possible elements that belong to A or B or both A and B. So it's talking about every single thing. So if I'm talking about the union, I'm talking about all of the set that's in green. So A union B is in green, and set of all X such that X is an element in A or X is in the element of B. It's an or because it's saying it's either in one or the other, and it could also be in both. Whereas the upside down U is the intersection. That's just talking about what they both share, what's common in both of them. So now it's only where they both intersect, which is now this shaded green area. So now it's X is in the set of A and X is in the set of B, versus before it was in at least one of those two sets. If we have disjoint sets, they do not have anything in common. Okay, they do not share anything. Their union, you're looking at, I should say your intersection is no solution. They do not intersect at all. Okay, they are mutually exclusive. Mutually exclusive means they do not share anything. They do not control one another. So here's a quick little example. A is a set of all factors of 36. B is a set of all factors of 54. Find the union. Find all the different possible values that fit in one or both. And then find the intersection, the ones that just, they both overlap. So take a moment, do the factors. So now that I have all the factors listed, I should be able to do the union. The union is every single number that should be included. So every number should be written once. And then the intersection is just those specific numbers that they share. So each of the numbers that they share are just those 6 numbers. So when you take a look, put them all together. Hopefully I didn't miss any initially. For the union, and then the intersection are just the two that they both have, or the numbers that they both have in common. We can look at, within the Venn diagrams, being able to distinctly talk about different pieces, such as in part A, it needs to be in A but not in B. So not B means I cannot include any of B, but it has to be in A. So the only thing that's in A is this portion here, but it doesn't include anything that they cover. So I'm going to pull that part out. So it should only be in A, but it can't be in any part of B. So sometimes it's a little easier to look at what it can't be in. Whereas in the second one, it can't be in A or in B. It's in neither of those. So I can't have anything in A or anything in B, which means it's everything outside of them. So I'll get rid of that region there. So just taking a look at what does it mean by wording, excluding, including pieces of information. We can use Venn diagrams to figure out numbers of people, which then means in turn you can find some individual probabilities. So if you take a look at this Venn diagram, I'm just going to talk about a couple of pieces of information. T is tennis, H is hockey. So if I look at the whole picture, there are 7 individuals that are outside here, which means 7 of the people that were in this sporting club are not in tennis or hockey. 27 are in the middle, so 27 play tennis and hockey both. 15 only play tennis, so I can add those 2 numbers up to find all of my tennis players. And then 26 are only in hockey. And then since they're only in hockey, I can also add that middle part for how many people play in both of them. So to find the total in the club, just add up all of the numbers. 15 plus 27 plus 26 plus 7. There are 75 individuals in this club. Number in hockey is all of those. So add up those 2 numbers and I get 53. How many play both sports? Both sports is only going to be the overlap. So there's 27. Neither of these sports, that's this outside number 7. At least one sport is going to be your 15, your 27, and your 26, because it's at least one sport. So I can also include the people that play both, only once though. So that's 68, folks. And those who only play one sport are the 15 and the 26, making 41. So based on a Venn diagram, you're able to answer some questions about it. Okay, and then again, in this case too, it may be helpful to draw your Venn diagram. So we have a class of 30 students. And I have physics, and I have chemistry. So 19 total people studied for physics, 17 total studied for chemistry, and 15 studied for both. It may help to start with the both, because if 15 of them studied for both, of the 19 who studied for physics, there were 4 that only studied for physics. And of the 15 who studied for both, there were 17 total who studied chemistry. Therefore, there's only 2 that studied chemistry. So 4 plus 15 plus 2 is 21. So 9 did not study either of those. So from this Venn diagram, I'll now answer my questions. I like to visually see what I'm taking a look at. So the number that studied both subjects, and again, we're looking at probabilities now, not just the total number. So the probability is the part over your whole. So how many studied both? 15 out of the 30, which then becomes a half. At least one subject, adding those up. 4 plus 15 plus 2 is 21 out of 30, which that becomes 7 tenths. Physics, but not chemistry. So 4 people studied physics, but not a combination of both. So 4 out of the 30, which becomes 2/15. Exactly one of the subjects. So either just physics or just chemistry. There's 6 of them out of 30, which becomes 1/5. Neither subject, we calculated that already, 9 out of 30, which is 3/10. And then lastly, chemistry, if it is known that the student studies physics. Now what I'm doing is I'm changing my total amount of people I'm using. I have to look at known that the student studies physics. So there are only 19 folks that studied physics, and of them, 15 also did chemistry. So now my probability is 15 out of 19. This we're going to get into a little bit more in depth in the next section. It's more of what's called a given statement. The probability of C given P is how we'll talk about it to try to help ourselves out. So with all this information, we've gone back through, we've done our binomial probabilities, and we used our Venn diagrams to both find numbers and then also find individual probabilities.